My name is Idil Shamiloglu. I'm a distinguished professor in electrical and computer engineering here at the University of New Mexico. I'm also the Associate Dean for Research and Innovation in the School of Engineering. I've been at the University of New Mexico my entire career. I came here as an assistant professor in January of 1988, and I helped found the Applied Electromagnetics program, both at the undergraduate and the graduate level. The Applied Electromagnetics group is one of the most robust groups in the School of Engineering. We are one of the top electromagnetics programs in the country. We are very large. There are 5 faculty in Applied Electromagnetics. Besides myself, there's Professor Christos Christodoulou, who's the Dean of Engineering. There's Professor Mark Gilmore. There is Professor Jane Lair, and there's Professor Zhen Peng. We together bring in probably the most funding of any area in the School of Engineering and at the university. My particular expertise is in a field called plasma physics, and the subfield is in generating high-power microwaves. By high-power microwaves, I mean very large powers. To put it in perspective, your microwave oven at home produces on the order of 1 to 2 kilowatts of power. The generators that I study in my laboratory generate over 1 billion watts of power. Of course, whereas your microwave oven at home can operate continuously for minutes at a time, these very high power sources can only operate for very short periods of time, typically on the order of 10 to 100 nanoseconds. The technology that we use to generate these sources of high power microwaves is called pulse power technology. Pulse power is basically a technique where you accumulate energy over a relatively long period of time and then you release it over a very short period of time. As you all know, power is energy divided by time. So if I accumulate power gradually over a long period of time, if I release it in a very short period of time, I can generate extremely high power levels. And pulse power technology is an important technology in the state of New Mexico. At Sandia National Laboratories, there is the Z machine. The Z machine is the most powerful pulse power machine in the world. It generates over 200 terawatts of power. And pulse power is also important to Los Alamos National Lab and the Air Force Research Lab. The Air Force Research Lab here in Albuquerque has a very robust program in directed energy, and high power microwaves is one of the important pillars of directed energy. In my laboratory, which you will shortly see, I have several graduate students who are working on their master's and their PhD projects. But in addition, I have several undergraduates. Typically, I hire undergrads beginning in their sophomore and junior years, and they spend time up to 20 hours a week working with my graduate students in the laboratory. And because of that experience, many of my undergraduates then decide that they want a master's and a PhD, and they are hooked and proceed with their education, something that they thought they may not be interested in doing previously. So I hope you enjoy this video and the video of the other faculty in Applied Electromagnetics, and that you will learn more about what we do here in the Department of Electrical and Computer Engineering at the University of New Mexico. We are now in my laboratory. This is the UNM Pulse Power Beams and Microwaves Laboratory, part of the Applied Electromagnetics program. As an example, this is a CAD drawing of one of my 2 accelerators in the laboratory. This is an accelerator that's called the Sinus 6. It was built by the Institute of High Current Electronics of the Siberian branch of the Russian Academy of Sciences. Back in the early 90s, I visited Russia after the fall of the Soviet Union and established a collaboration with a group there. And as part of that, we were able to acquire one of their accelerators. As I mentioned earlier, my main line of research as a plasma physicist and in the subfield of high power microwaves is we generate intense relativistic electron beams, and then we take those electrons and we convert their kinetic energy to microwaves. And that's the basis of my laboratory. So as an example, this whole technology here is required to make the high voltage pulse, but the high power microwave source itself is actually quite compact. It is this region here. This is a solenoidal magnetic field, and the whole source is in there. So in this region is where electrons give up their kinetic energy and generate microwaves, and then finally the microwaves are radiated. So basically, we perform a lot of simulations using what's called a particle in cell tool. Particle in cell is basically a finite difference time domain code that self-consistently solves relativistic kinematics, and we use these tools to optimize the design of sources. So basically what we do is we are pushing the state-of-the-art in the generation of these high-power sources. In fact, my laboratory is the premier university laboratory in the country that studies this field. Let's go and take a look at the hardware. So here we have two accelerators. This is the Sinus 6 accelerator that we've had since 1992. All this technology here that you see is what's required to basically generate a high power, high voltage pulse. The pulse comes down the line and then comes to the load region, and here is where we would normally have our high power microwave source. The high power microwave source itself is fairly compact, about the size of a Coke can, and we use a guide magnetic field to allow the electron beam to propagate in vacuum and not blow apart. Here we have another accelerator. This is a what's called a pulse rad. This was manufactured by Physics International Corporation, which is now L3 Physics International. This was actually purchased by Sandia National Labs, and in the early 1990s, they donated this to my laboratory. My former student and postdoc and research professor, Sarita Prasad, designed this front end, which is the pulse forming line. Basically, what this allows us to do is generate a voltage pulse with a very, very fast rising edge. With a very fast rising edge, we're able to study relativistic magnetron and achieve a region of operation that no one else in the world is able to do. Let's see if I can show you some of our sources here. Let's come this way. This is an example of one of our high power microwave sources. This is called a relativistic magnetron. It's very similar to what's in your microwave oven, except this generates 1 billion watts of power. You can see by looking on the inside, it's a very simple passive structure. It's basically an anode block with vanes. And as electrons rotate around those vanes, the electron phase velocity is synchronous with the phase velocity of an electromagnetic mode that's contained in that cavity. And that is where we generate the microwaves, and then we extract it radially using waveguide. This is an example of another one of our sources. This is a very crude version. We built this as a quick and dirty test source. The technology that my students use is called water jet cutting, and this is basically a metamaterial slow wave structure. This basically is comprised of split ring resonators, a biperiodic array of split ring resonators, and it's inside a below cutoff waveguide. So it's hard to imagine, but with this structure, we generate 1.4 gigahertz. What's unusual about that is the half wavelength for 1.4 gigahertz is about this big, and this should not fit in here. This is below cutoff. But being below cutoff gives it a negative permittivity, and having the split ring resonators in there has negative permeability. After we tested this, everything looked great. We had it professionally machined by a local machine company, and we hold the world's record of 100 megawatt generated using a metamaterial slow wave structure. Here's an example of our magnetron with diffraction output. This is very similar to the magnetron you were shown previously, except it has this large antenna and diffraction output. And this holds the world's record right now for the largest efficiency generated from a magnetron. We hold an efficiency about 70%. And then finally, as part of a DARPA award, this is a high frequency slow wave structure that, believe it or not, we 3D printed and copper plated. And we're about to begin experiments with this, but we're predicting 100 megawatts in E band, which is about 75 gigahertz, to be generated from this. If we're successful, that would be a world record for any microwave generated using a 3D printed slow wave structure. As I mentioned previously, Sandia Labs holds the world's largest pulse power machine, and here is a photograph of it, time integrated with the lids removed. You can see that this is called the famous arcs and sparks photograph of the Z machine. This basically is 200 terawatts of power, and when you have such high powers, you can't use cables, you can't use things that are traditionally used in laboratories. So hence, the pulse forming lines are in water, and as the power flow goes through the water, you can see all the arcs and sparks. Finally, this is a calorimeter. We use this to measure total energy generated in our microwaves. The way this works is we fill it with alcohol, and then as the microwaves go through it, it heats the alcohol, and as the alcohol is heated, there's a sensor here that can detect the expansion in volume. And once we know the expansion in volume, we can correlate it with thermal energy. And this I'm pointing out because this was a ECE senior design project a few years ago. And so there we have it, the Pulse Power Beams and Microwaves Laboratory at the Department of Electrical and Computer Engineering, University of New Mexico.
Hello, my name is Christos Christodoulou. I'm the Dean for the School of Engineering, but I'm also a faculty in Electrical and Computer Engineering. I belong to the Applied Electromagnetics group, and my specific area of research or specialization is in the area of antennas and RF circuits. So basically, we work with building antennas for communications on the ground, like cell phones. In fact, talking about cell phones, the new iPhone XR or X, one of the antennas has been designed by one of our students, my student, who graduated from our program here. I also want to show you the Fitbit. This antenna here was designed by one of my PhD students who work for Fitbit. So our students basically have been very successful out there in industry. And we also have a center here called COSMIAC, which we have a lot of, we track satellites, low Earth orbit satellites. We have a whole ground station, and we track satellites 24/7. We do a lot of space communication, space electronics, mainly in my area RF, which means not very high frequencies optics, but we do work for, let's say, from 500 megahertz to, at least in my research, 80 to 90 gigahertz. We got projects, and we would be more than happy to include, and we do include, not only graduate students. Of course, we're very big in research. We're an R1 research university, and we bring a lot of research money, but also we like to involve not only undergraduate, even high school students if possible. I personally hire like 400 to 500 graduate students, I should say high school students, every year, because I want them to get them involved in my research. So any undergraduate student will be interested in working with me. We got some amazing facilities. We're even getting some other new equipment. And basically, I believe when it comes to antennas, we have one of the top 5, we'll say top 10, just to be sure, programs in the country, very well known. And we can build, we can test, we have state-of-the-art equipment. We work with the Air Force, Sandia, Los Alamos, NASA, and a multitude of companies. So anybody who is interested, remember, RF, cell phones, satellite communications, everything you're using on a daily basis. That's it. So I'm looking forward to get some volunteers. Actually, forget the volunteers. We'll pay you to work with us. Thank you very much. All right, so this is what we call the anechoic chamber, no echo. In reality means no reflections from the walls. So when we study an antenna, let's say you have a cell phone, you have an antenna on a UAV, we put the antenna right here. This is a turntable and it rotates. We have a source coming in down that way, another antenna that transmits electromagnetic energy. And then we study the behavior of the antenna. Does this antenna behave the way we simulated, the way we designed it? If not, we go back and we redesign it. But before you use any antenna, whether it's on your car, your cell phone, your computer, in an airplane, on a satellite or anything, you have to make sure that you test it. Otherwise, you cannot guarantee simply from the simulations, the computational tools that we got in here, that it's going to work. So this is what you need, and we're one of the few universities in the country that has this anechoic chamber. This is a compact range. We also have another one that we're building. It's called near field facility for measuring something called array antennas, like an array of little antennas that you can use to do a lot of things. Here is called a network analyzer. This network analyzer is one of the latest brands, and it's like 450,000, just this box there. Of course, it controls everything, and it lets us characterize some very complex electromagnetic, or we call them RF, radio frequency structures. And it depends how big and small your equipment or your antenna is. We can actually fabricate it, design it, fabricate it, and test it right here in our university. So here's another, we try to combine power, and we're gonna connect antenna elements right here. This will be the feed structure. So we can build, design very complex, and our students here, by the way, we do have undergraduate students that come in here, and what they do, they build their own antennas. Let me show you this piece over here. This is instead of using chemical etching, etc., we can build planar structures. Those are the structures that go on flat, on a computer or a cell phone, but we can build it here, so the students can actually go. We have a different room to do the computational analysis. They actually print the antenna here, and then they take it and test it here, and then do another set of tests. So we had students, undergraduate students, who built the whole thing, and by the end of the day, when they finish, we'll let them keep the antenna for them as a souvenir, because we can build a lot of those. Those are what we call microstrip antennas. The other more complicated three-dimensional structure are more complicated. However, we also work with Cosmic, and we have a lot of 3D printers. So we have built antennas that are 3D printed. You have to electroplate them to make them conductive. But our students have a lot of fun when they come in here.
Hello everyone, my name is Mark Gilmore. It's a pleasure to introduce myself to you. I'm a professor here in the Electrical and Computer Engineering Department at the University of New Mexico. Let's see, I came to UNM in 2003, so I've now been here 15 years this year. Generally, I am in the area of electromagnetics, so I teach courses in electromagnetics and do research in that area. Specifically, my research is dedicated to plasma physics and fusion, nuclear fusion for energy. Plasma plasma physics is a specialized field. It's not very large worldwide, but there's actually a lot of plasma physics here in the state of New Mexico. So if you're interested in staying in New Mexico, this might be an area you want to consider. Plasma is ionized gas. So it's gas where the electrons have been stripped away from the neutral atoms. So it's electrically conducting. It behaves like a gas, but it also responds to electric and magnetic fields. So it's a complicated state of matter. There are many applications in natural science, in physics, astrophysics, fusion for energy, and there are also a number of engineering applications as well. So this is our machine shop where we build a lot of the stuff we need for experiments. Come on through, Tim. This is a graduate student. Welcome to the Plasma and Fusion Science Lab here at UNM. As I told you before, my name is Mark Gilmore, and the research that my group does, about half of it is off-site at Sandia and Los Alamos labs. So we send both graduate and undergraduate students to those labs to work on research. And then about the other half of it is done here in my lab at UNM. And our primary experiments are done on this device here. This device is called Hellcat. Let's see, maybe I can give us a better view. By opening the Faraday cage. So what we're looking at now is an argon plasma. Argon makes that nice bright blue color. The color of a plasma depends on the type of gas and the temperature of the gas. So you may be familiar with neon lights, that nice vibrant orangish red color. So that's a typical color of neon. And argon makes this nice deep blue. So we're making the plasma in this case with what's called the helicon source. So the helicon source is an RF or radio frequency source. So we put some RF power on the antenna you can see here. If you see a glass tube sticking out of the end and wrapped around it is some copper, that's actually a helical shape. And we put a few kilowatts of radio frequency voltage on the antenna at about 10 megahertz. So the few kilowatts is about the power of a small radio station. So we're putting relatively a lot of power into a relatively small volume. So the electric fields from the radio frequency voltage accelerate electrons, they collide with neutral gas atoms, knock off other electrons, and form the plasma. And so in this device, what we study is basic plasma physics. This is one of about 15 such devices in the world. It was built with funding from National Science Foundation and Department of Energy. And we look at the basic physics of problems related to both engineering and astrophysics. So for example, we're trying to understand how turbulence in the plasma forms and can be controlled. Turbulence, it turns out, is important in transporting heat and particles. And that's an important problem in nuclear fusion for energy. So right now the heat and particle transport is too high, is one of the reasons that fusion energy is not yet working. So we're trying to understand how to control the turbulence and the transport of heat.
Hi, my name is Jane Lair. I'm a member of the Applied Electromagnetic faculty here at the University of New Mexico. I specialize in high voltage engineering and pulse power and applied transient plasma physics. The courses I teach for undergraduates are Applied Electromagnetic for Engineers, the undergraduate electromagnetics course, some specialty graduate courses in pulse power, microwave engineering. I'm planning an instrumentation course, and pretty much anything that deals with design, which I'm particularly fascinated by. My research lab is called Aperiodic. It's an acronym for Applied Pulse Energy Discharge and Ionization Center. We tried to come up with an acronym that really encompasses all the different areas that we're involved in researching. So what I'm particularly interested in is the intersection of physics with engineering. That is, how do I use my knowledge of physics in order to solve problems, make products and components. Much of my research is involved in things like directed energy and other high voltage engineering, but I'm also moving into different areas such as power electronics, which is undergoing a revolution right now because the wide bandgap semiconductors are allowing power electronics to be used at higher voltages and higher pulse repetition rates, which is where my expertise comes in. For undergraduate opportunities, I also am the faculty advisor and teach classes in two engineering competitions. One of them is the Solar Splash, which is the largest solar boat regatta in the world. We compete in June of every year so far. This is a senior design option as well as a track elective option that's joint with the mechanical engineering department, where we make a boat that is completely solar powered. So that means that we take solar panels and we energize them from batteries that are recharged from the solar panels to power the boat. It's not completely photovoltaic, in that there are many, many subsystems that have to go on, such as a motor controller or an energy optimizer that encompasses all different disciplines of electrical and computer engineering, including software engineering. The other competition, which I am also the faculty advisor, is the FSAE, the Formula Society Automotive Engineering, also joint with ME. And we're pursuing an electric vehicle. So that we're just starting that. We're not even competing this year. We're only doing the design work. We plan to compete the next year. But that again offers opportunities in both senior design, track elective, and there's a graduate option. And this, the reason I do this is I really enjoy design. But I like to encourage students, and this is a great way to do that, where students are encouraged to get their hands dirty, make some mistakes, and also let their creativity flourish. They're also, it's a way to explore professional behavior, where you have to attend meetings, you have to work in teams, you have to solve conflicts. There aren't many of those, but sometimes people want to take two different design paths, and how do you negotiate those sorts of decisions in a respectful manner with your colleagues? And that's something that is absolutely a critical skill for an engineer.
My name is Cameron Pouncey. I'm a grad student in the Aperiodic lab under Professor Jane Lair, and we do high power electromagnetics, pulse power, high voltage engineering, and other fun things that involve really high voltages and then blowing things up with electricity. So, in this lab this is our pulse power experiments lab. We do a lot of things like build and test Marx generators and other high voltage pulse equipment. and do experiments that have to do with things like dielectric breakdown of different materials and physics of sparks and that sort of thing. So over here, this is an experiment that another grad student was working on. It's kind of hidden inside this copper mesh because his machine was messing up my computer. So this is a pulsar that generates 500,000 volt pulses in only 2 nanoseconds. So we're testing the breakdown of seawater using that. He's doing some different experiments there. And as you can see, our stuff is big, you know, lots of wires and all of that. Then, let's see, back behind me, we're doing some switch testing and stuff. It's kind of a mess right now, but, so we're testing some spark gap switches and different equipment. So as you can see, our work involves lots of oscilloscopes and lots of probes and high voltage stuff and the occasional piece of Tupperware. One of the most interesting things to me about this line of research is you have to make all of your own equipment for the most part because nobody sells this stuff in stores because it's kind of an unusual field. This is a Marx generator. It's a device that generates high voltage pulses by charging a bunch of capacitors in parallel and then discharging them in series. It's called Harpo Marx because we have so many of them we started giving them names. So this one is portable. It's on wheels. It's got a battery. We can just roll it around. And so I'll charge it up and fire it for you guys. You can see how it works. And hopefully Gunny doesn't jump too bad.
Okay.
And hopefully it doesn't ruin his camera.
No, it'll be fine.
Alright, so that's 7,000 volts we've charged it to. 8,000. 9,000. 10,000. 11,000. 12,000. Alright, and I'm going to fire it and hopefully it works. In 3, 2, 1, fire.
Whoa.
Yeah, sparks are fun. Zapping stuff is fun. One more time.
Sure. Wow. That is pretty cool.
Hopefully it shows up in the shot because the sparks are only there for about a microsecond, so it can actually sometimes not show up in the film because the camera shutter will miss it in between frames. But most of the time you get it. Anyway, so one more time, just for fun. Ow. So anyway, so that's the kind of stuff that we build and do here. So this is our, like I said, we have to build a lot of our own instruments and stuff. So this is our fabrication shop. We have a couple of workbenches with various things set up. Some oscilloscopes and meters and that sort of thing. Microscope over here so we can look at especially electrodes and stuff like that because they get damaged from the sparks. That's a 10,000 volt voltmeter. And then we have, over here we've got our miniature CNC machining setup. So we can make various parts, complex parts using computer controlled milling machine and lathe. This is an attempt at making a sign for one of our new lab rooms. I had a couple of undergrads working on this and it doesn't quite line up, but they're still trying. So they did that on this CNC machine. Did the solid 3D model to make the sign, and then set it up on the machine, and didn't quite get it right, but they're getting there. They'll get it on the next one, I'm sure. And then over here we have our Formlabs 3D SLA printer, so we can print fairly complex pieces out of a resin. It's a resin that's hardened by UV light, and so you build things up. Unlike the little extrusions the extrusion machines, you can make much more complex things. Like this is a little block with spirals actually inside the block of solid material. Let's see, I can show you another part. This is a piece that I just made. It's a pretty complicated thing that you couldn't really make normal machining. It's a bobbin to wind wires on for a transformer, and then 2 capacitors go in here, and so it's a pretty complex piece of plastic, and it took about 8 hours for the machine to grow that. But yeah, it's a really interesting capability that we've had for about a year now, and it's proven to be really useful for the stuff that we do. And then we even have, we have welding equipment and all kind of things. We build circuits for the stuff that we do, pulse power and everything are physically big things. I mean, the circuits are like the Marx generator. I mean, it's a circuit, but it's made out of big pieces, and so you sometimes have to weld stuff.
But we also have to do the auxiliary,
Yeah.
small, so we'll do a lot of circuit design, but it's pretty much the lowest voltages we go to is about a kilovolt.
Yeah. 10,000 volts is low.
Yeah.
Hello, welcome to Electrical and Computer Engineering at UNM. My name is Zhen Peng. I joined UNM as a faculty member since 2013. So my background is electromagnetics. In way, electromagnetics actually provide the fundamental physics of wireless communication, including our cell phone communication to the base station, including the radar communication to the satellite. So we know that electromagnetic waves is invisible to our human eyes. That's the reason we need a computer to visualize the electromagnetic waves. So the research in our group in particular is to use computer to simulate electromagnetic phenomena. And if you are interested, we do have opportunities for undergraduate research. If you are interested in electromagnetics or computer engineering, you're welcome to join our group. We can do something very fancy together. So welcome back. Welcome back to the computational electromagnetics lab. As we discussed briefly, we can see we can utilize a computer to simulate very complicated electromagnetic phenomena. From these slides, we can see we have a look at aircraft carrier, extremely big scale problem. We're trying to analyze what are the antenna performance when we have multiple antennas installed on this aircraft carrier integrated island. So we are able to use computer to predict what is antenna performance and what is interference between different antennas.
Hi, my name is True. I'm a graduate student working on computational electromagnetics, basically applying high-performance computing, parallel computing to solving the time domain Maxwell equations.
Second student, Evelyn.
Hi, I'm Evelyn Domi. I do work on stochastic E&M. I specifically look at incumbent fields upon electromagnetic devices and stochastic processes therein. Thank you.
Hello, I'm Omi. My research is about combining machine learning methods with conventional computational electromagnetic computational electromagnetics, and also I'm beginning to work on hardware acceleration for computational electromagnetics. Yeah.
My name is Shen Lin. Is the graduate student working on a totally new world. It's stochastic EM is a chaos. Is a chaos different from the older world we have ever seen here.
It is pretty much the overview of our lab, and if you are interested in some of the computer simulation of electromagnetic phenomena, you're welcome to contact us. We have a lot of opportunities to working together.